masses, and we draw a little cloud of them, not too many. There is the position of the ith particle r sub I. It's got its little mass there, and there's a whole bunch of these. And Newton's law, we just label everything with that subscript. F sub I equals 1 to n, and n could be as large as 1. Okay, so system of point masses. First thing we did was break this force on the ith particle up into an external and internal force, which is convenient. So I'll write 4 m sub I r sub I, two dots. The external force plus then the sum of all the internal forces, J equals 1 to n, J is not equal to I. And so here the idea is this whole cloud of particles could be subject to an external force, like gravity in this room. But they're also interacting with each other. So that's the way this is set up. And right, we had this before. And the next step was to sum over all of these. So then we look at, you know, if we have an equality here, then we also have an equality here. Sum over all of the external I, and now we have a double sum I j f sub I j. And I'm going to get more explicit with, have explicit examples of this in a moment. But first we'll just go through the calculation we had before. So we've got this sum over all of these possibilities, and I'll write I not equal to j. And so because of that, this double sum here can be broken down into pairs. And this statement, Ij and Ji, just expresses Newton's third law. So if we had two particles here, you know, this is the m sub j right here, and the interaction force between the two, we're assuming goes like that, and they add up to 0. And because of that, this double sum equals 0, and we had sum over m sub I or sub I second derivative equals the net external force on the system. Okay, so that's what we would ended up with. And then we said, okay, this is the derivative. This is a time derivative, complete time derivative of the expression with one fewer derivative. So we would have d over dt of m sub I r sub I dot equals the net external force. If the net external force is 0, then this sum is what? The derivative is 0, so then that sum is a constant. And this is how we already got the conservation of linear momentum for a system of point particles. So this is very important. I'll circle it in red, and I'll just continue that comment. We had this last week, but it's all right. If the net external force is equal to 0, comma, then mi dot equals constant, and that is for the lowercase p sub I, which we could call uppercase P, the total linear momentum, is constant. Is constant. So this whole idea is conservation of linear momentum. Linear momentum. So we're going to take off, this is what we ended up with last time. And this sum of forces can be unimaginably complicated. Okay? And they all cancel, and therefore, so some collision, I like an example, some collision of some really complicated object, like Starship Enterprise and something else. Okay? There's just all manner of twisting, crunching, and everything else going on. All those things from the standpoint of the external force, or from the standpoint of standing away from it a bit, all those forces add up to exactly zero. And so this giant collision with all that's happening is just a simple conservation of linear momentum. And you guys probably remember doing conservation of linear momentum to some degree, collisions in physics 4A. You might remember things coming in at an angle to each other, combining, continuing on straight. We're going to do more of that formal stuff, more formal version of what you've seen before later on. But there's our conservation law of linear momentum. So we can do some more interesting things here now. And remember, the individual mass times velocity is a simple linear momentum of one particle. Here it's the linear momentum of the entire cloud, so to speak, the entire system. So next, this is a good place to introduce, so we'll leave that up. Introduce the center of mass that we've mentioned a few times. So next, center of mass, I'm just going to define it. I'll just call it R without a subscript. It's defined as the sum of these moments divided by the total mass. Okay. That's the center of mass. Let's make sure. When's the last time you guys calculated centers of mass? Let's make sure we see the very simplest application of this before we continue on. So, suppose you're on the number line here. 0, 1, 2, 3, 4, 5. And just for the sake of argument, we'll put a single mass here and a single mass right there, the 2 and the 5. So where's the center of mass going to be? Just based on intuition. 3.5. 3.5, exactly. Like draw a little star there. If we're going to calculate x center of mass, according to this formula, we'll just take the x components. We would have m times 2 meters plus m times 5 meters divided by m plus m. So I've just applied this definition. And what do we end up with here? 2, 5, 7 m meters over 2 m. You get 3.5. Okay. So this always works. It doesn't matter when you flip the origin. And it works in x, it works in y, and this is of course just the balance point. Yeah.
So basically, this is just like an average.
Yeah. But it's weighted, right? Because you have the masses times the components. So that's the definition of the center of mass that works for everything. Another example, we should even put this one on the homework just for, we will, in fact, why not? Because you guys may not have done this. Suppose you have Earth and Moon. Our Earth and our Moon. Okay. Where's the center of mass of that system located? You can take the origin as the center of Earth if you want. So I'm going to call this a homework problem. You have to plug in a couple of numbers, right? You need the masses of Earth and Moon respectively and their center to center distances. So calculate center of mass of Earth-Moon system. Actually, it doesn't matter where you put the origin, you're going to get the same location. You may as well just put the origin in the center of Earth. Yeah. Anybody know the answer to this, roughly?
Guessing just a little ways on the Earth.
It's actually inside the Earth, center mass of the two. But you got to plug the numbers in to know that, right? So that's why this is a worthwhile thing. And then the center mass of the solar system is more complicated, right? But it wanders around a little bit too. It may be within the sun or without the sun. Look that up or figure it out. Okay. So yeah, that's your center of mass. It's your balance point, and
I'm guessing this has something to do with tides.
yes, a very famous part of the explanation of the tides. So I'll just put another example here. Say you have some object like this, and if it were a uniform object, you just eyeball it and say the center of mass is roughly there, right? It would actually be the balance point. If it's a uniform flat object, you could balance it across that line, you could balance it across that line. And the center of mass of California, anybody know where that is?
Not too far from here.
Not too far from here. I think it's up in North Fork. Wouldn't they? City fathers put it on the sign outside. Welcome to the center of mass. But good. So this is how these are calculated, and of course there are integral expressions for this too. We'll be doing more of those next semester, locating certain centers of mass when we're doing rigid body motion. But for now, we need this fact because it's going to have an interesting application with that differential equation we have right here. So I'm going to go ahead and erase this center of mass discussion or picture right here. So if we have the center of mass, so now take R, well, I'll label it center of mass for the moment, okay, COM. And do the following. We would have, and let M equal the sum of all of those individual masses. Then we have taken our definition, one step at a time, sum of M sub I, parentheses around there, bar, center of mass, equals sum of M sub I, bar sub I. And we can take two derivatives of this and not change anything, okay? But now this, I can go to there and I'll take the left side of this and I get capital M R center of mass, second derivative is equal to the net external force. So what is this? This is just a fancy looking Newton's law that we've been studying this whole time. Okay. Say if you throw a baseball is an extended body that's made up of many particles. Right? We treat it as a point mass. What this is saying though is that the center of mass moves as though the net external force were concentrated there. So with the baseball, there's no surprise, but what about with the horseshoe? Where's the center of mass of a horseshoe?
Like in the middle of the horseshoe where there's not actually the horseshoe at all.
Exactly. So I should have put that on my, we're gonna calculate these next semester.
The real question is, will this discussion make me better at horseshoes?
Yes. This discussion will make you better. Yeah, so let's go with the example here. So the horseshoe looks like this. Okay. And if we put this in a coordinate system, actually the center of mass, if you want to balance this thing one way or the other, you're going to find, say you cover it with a thin film or something, balance it on a string. Yeah, you're going to locate the center of mass somewhere right here. Okay. So when you throw the horseshoe, it can tumble and do what it does. It's a nice iron one, so wind resistance, no problem. But it's this point here that's actually moving along a parabola, right? This point here describes the parabola. So the high jumpers actually made use of this fact when they introduced the modern, which is not that new anymore, the modern way of jumping over a bar where they, for a high jumper, you just take this horseshoe and put, feet on one end and arms on this end, right? And they're trying to go like that over the bar. You guys recognize that in the picture? So they're trying to pass over the bar like that. There's the nose. And, if they're good, their center of mass is actually passing under the bar while they move over the bar like that. So the same thing holds for a human. As soon as you leave the, say, diving board or whatever, your center of mass is you can be twisting and turning, and what you do, center of mass is what's moving in a parabolic trajectory. So yeah, we have that out of this discussion. So that's an interesting point of view. So we'll put a couple words here. It's the center of mass that moves as though the net external force were acting at that point, even though there's actually nothing at that point. That external acting on it, acting. All right, at that point. Yeah, what do you think of that? Annuity? Good one. And again, this is just the form of Newton's law that we've started out with. Since we're doing point mechanics and everything's composed of a myriad of individual little particles, and we have to be able to reconcile all the basics with that new point of view. Good. So yeah, you guys can calculate this. That'll be good. Centers of mass, we'll calculate next semester more of those. Okay, let's see. Oh yeah, as far as the concrete example, I'm going to write down the two particle potential energy next. I'm going to need that. So the next example is two particles, and this is what we've been doing when we started the central force problem. I actually went to two particles, did a quick derivation of this. We're just going to look at that again. Two particles and gravity, let's put it that way. And we have what I'm going to introduce now, U of R1 their respective positions. 2, right? M1 and M2. And what does this potential energy function look like? Minus G M1 M2 over R1 minus R2. This is our negative alpha over R, essentially, right? Because this is the separation distance between the two particles. How do we get from here to the force? Newton's law of gravity. This is the, we call it the Newton potential for two particles. How do we get to the force?
Integrate this.
The opposite.
Right.
Differentiate, right?
Sorry.
So here's what we want though. We want to get, I'm going to call this F sub 1. So if we wanted the force on the first particle, we're going to do minus the gradient of this thing. And when I say the gradient, these are R's. Okay. I have to specify a gradient with respect to which particle. So we'll call this gradient sub 1. Okay. And then I can go ahead and do my calculation. Minus minus is plus. I get G M1 M2. And this gradient here with respect to the first particle, that's just going to give us a minus 1 over R1 minus R2 squared, and then it's going to give us a vector. So this is the same thing that we've been doing recently, because what I'm writing down here next, R1 minus R2, this is the unit vector. Okay, this is a unit vector. What is it pointing at? It's pointing at R1, right? R1 minus R2 is pointing this way. The minus sign in front tells me that the actual vector is pointing the opposite direction. And that's the attraction of this particle to the second one, the gravitational attraction. So everything's in there. Now F sub 2 is going to be minus gradient with respect to the second particle of this potential energy. But what's the only difference in those two calculations? The only difference is that the chain rule is going to give me one more minus sign. Right? It's going to give me a minus sign when I do the final chain rule, because I'm differentiating with respect to R2 instead of R1. So giving me one more minus sign really will give me minus F1. This is one of those, the example where I was saying the two internal forces, you add them up, they cancel by Newton's third law. So this is the explicit version of that. I'm going to put a couple of notes here to make sure you make contact with what we've done before. Remember we had gradient of minus 1 over R. Okay. Was minus gradient of 1 over R minus this R to the negative 1, so minus 1 R squared R over R. So we did those calculations, right? And you can't do these too often. You want to do them often, and electricity and magnetism, you're going to be knocking them out again and again as well. But this calculation that we have practiced, and we should practice some more, is exactly what was going on here. Right? I just have chosen a different origin. I have a certain origin. Instead of calling the origin 0, it's at one of those points. So yeah, these calculations you have to practice, and remember, the gradient of R was the unit vector. We did that calculation as well. So put these on your list of things to do, just to practice that. And even to remind you here, d dx of I of the square root of x1 squared plus x2 squared plus x3 squared. Remember, that's what this was here. The left side, there's the I of 1, you add 1/2, you add this thing to the minus 1/2, and then you always took the inner derivative of x of I over 1. So you practice these a few times to start to see them. But here I'm making the point that for this explicit example, for this specific important example, we see how those two forces, equal and opposite, comes out if the formula doesn't match. So I'll put that in some words here. So Newton's third law is satisfied. And that's what we had just done previously. That's why when we add all the internal forces, they all sum up to 0. This was an example of those internal forces. Now, if these two particles are, say they're the Earth and the Moon, but the external force is the sun, from the sun, right, then they're still both subject to the sun. Even though these two cancel. Okay, I'm tempted to do a bigger version of this. Namely, what if we have that whole cloud of particles, many instead of just two? We can actually generalize this thing here. So, for many particles, we're going to call this one here f sub I, and we'll have minus g. See, I'm going to call the 1 the I, right? 1 is the I, so we'll have minus g m sub I. We do the whole thing. So we'll have, I'm going to do a summation. So we'll have minus g m sub I, and this 2 would have been a j, m sub j, r sub I minus r sub j, and I'll take these together for the third power, r sub I minus r sub j cubed. You guys won't mind that, right? I equals 1, no, j. J equals 1 to n, and j is not equal to I. So that went pretty fast, right? I just took this one that's very clear from being a two-particle problem, and I'm just summing over all the possible j's out there. Now see, this was u of R1 and R2. We're going to do u of R1 all the way out to Rn. Now this one's kind of tricky. You could just take, you're going to leave some room out front, okay? You'd have minus g mi mj over ri minus rj. And what you do is you do a 2, you can see where the double sum, where the 1/2 comes from. For 1 and 2, you're adding them twice. You've got a 1 minus 2 and a 2 minus 1. Okay. So this, I may not assign it this semester. If you're ambitious, you can show that the kth gradient, you gotta use, will give you f sub k up here. Let's keep this in our notes, we won't necessarily assign this one yet. But you can see this is an interesting generalization, and you basically just take this one here, but you do a double sum, which means because you're getting both of these individual ones twice, and then you take 1/2 of that. But I'll put here, and gradient, so minus gradients of k of u is equal to f sub k as given above here, as given by star. We're most concerned with the 2-particle one for now, okay? But this is a natural generalization. It's a pretty tricky derivative to take. Okay, but I had to introduce this thing here. Yeah. For the 2-particle problem, you know, I just showed this. So we want to go on to our next conservation law. So we have linear momentum now for a big system of particles. The next one is energy. So what we're going to do is just define the energy. It's the natural generalization of what we've done in the past with one particle, namely, we're going to add all of the kinetic energies okay, so we're right with that. We're okay with that. We've done this before. And we're going to take this potential energy of that form. And this was one of those examples where we have that there. So, just a natural generalization. Take all the kinetic energies. You have to have a potential energy function of this form. So what you have to have is where gradient sub k of u of R1 of Rn is equal to minus force on the kth particle. So you have to be able to, you have to have a function of this form that gives you the force as gradient sub k. So what I mean by gradient sub k, it's always the kth slot here. Kth particle, that's whose derivatives I take. Okay. So under these circumstances, if you have such a situation, and you take its complete time derivative, up here, you end up with 1/2 sum over 2 mi ri dot ri double dot. Remember, we've done that for one coordinate. I think we did that on homework. So this is just the whole sum of those. And then we have plus, and this is that major chain rule. I'm going to write it in this way first. du dr sub I dotted into dr sub I dt. Which of course is r dot, r sub I dot. And I can factor that out. R sub I dot product. 2's canceled. M sub I, R sub I, second derivative. And now I'll go ahead and call, this was just for optical purposes, this was the gradient of K equals minus F Newton's law. So this is, we saw that the first time with 1 degree of freedom, and we saw it with 3 degrees of freedom, and now we see it with the whole set of particles. Really always the same calculation. Right? This is M sub I, R sub I equals F. So this equals 0. And if this equals 0, then energy is conserved. So dE dt equals 0, energy is conserved. So the conservation of energy law holds in the same manner as we've already seen before. Of course, this is key. You have to have a potential energy function that does this, and then it's automatically fulfilled. And the example here was important because gravity is one of those most important examples. It has a potential energy function, fulfills all these things, and energy is conserved as well. Good. So there's one more conservation law. I don't think we'll finish it today. We'll set it up. What's the other major conservation law? We have linear momentum, we have energy. Mechanics. It starts with angular and it ends with momentum. Right? Angular momentum. So the angular momentum law for a point system, it's a little more involved in these, but also very interesting. When it comes to solving problems explicitly, analytically, the key is having conservation law. Without that, you're pretty much lost. So these play a big role, even though there are so many degrees of freedom now. By the way, so linear momentum is 3 numbers, right? It's a vector, energy is 1, and then angular momentum is another 3. So you basically have 7 conserved quantities in all of these systems. Good, so I'm going to erase this, and we'll set the angular momentum up and finish it on Wednesday. So, here's the next problem we'll set up. We're going to begin with Newton's law for the point system, the ith external force plus some J equals 1 to N F sub ij, so the internal forces. And this time we're going to do a cross product multiplication and sum. So we'll say R sub I cross M sub I, second derivative, R sub I cross F sub I external plus sum over R sub I cross F sub I j. J equals 1 to N. Yeah, so if this is a law, then so is this, right? Then we left a little room here. If this here is true, then if I do a sum over all these truths, it should also work. So here we're summing I equals 1 to N. And our task is to show that all of these vanish again. So what we'll do is we'll break it up into R sub I cross Fij plus R sub j cross Fji. So this double sum consists of a bunch of these expressions. And we have Newton's third law, so we can replace this with minus F sub Ji. So we can say R cross Fij plus R sub J cross negative Fij. And what we then can write is R sub I minus R sub J cross Fij. So this double sum turns into a whole collection of these. But can we claim that this vanishes? I bet you we claim that that vanishes, but it doesn't necessarily vanish. But it does vanish under a particular circumstance.
Vanishes under the condition where J and I can't be equal, right?
J and I can't be equal. That's right. J and I are not equal because we always have two different particles, right? We've got an I and a J. And we have particles as I drew here. But here, look, this is R sub I minus R sub J. We've been studying this just in preparation for this moment. Would the cross product between the force between these two particles and this vector that I've literally drawn here, that cross product vanish? So there's a force between these two particles, and there's the vector that joins them, particles, which is this one here. There is a circumstance under which this cross product would vanish. If that were a central force. Right? If that were a central force, then those vectors would be parallel. So I'll put that here, that's what we'll end with today. Equals 0, comma, if Fij is a central force. Now, not all forces are central forces, so we'll have to keep that in mind, but Wednesday we'll be able to set this up and draw our conclusions, similar to what we did before. So yeah, the point is, if you had just a bunch of central force interactions, then this double sum actually does vanish.
Gravity is a central force.
Gravity is, but the thing is, electromagnetic forces aren't all central, like the Lorentz force. And that makes a crucial difference, so we'll address both of those concerns. Good, on Wednesday.